So notice that the extra credit was polyatomic ion stuff. I mean, it was naming, but it was polyatomic ion. So maybe that's how we're gonna get you guys to memorize some of these polyatomic ions at each of them.
With fear.
Well, it's extra credit. You don't lose any
Fear.
points,
Yeah.
but you have everything to gain by memorizing them.
What is CR? I'm gonna call myself out. I don't remember. Chromium. I knew
There you go.
that.
But
Felt uncomfortable about it.
we'll talk about it after. Yeah. So we've done this, but I just want to review to make sure everybody's clear. We covered the 3 different types of cubic unit cells we're going to study: simple, body-centered, and face-centered cubic. Let's see if this website works. Wasn't working the other day. Nope, it's dead. All right, that's too bad. So basically, this was just showing how some of these have those crystal structures. Polonium was one of the unique metals that is simple cubic, which is rare for, and it's not really a metal. It's actually, it's one of those weird ones that is metallic, semi-metallic, but it's really, we're not sure because it's a synthetic. Like anything on the periodic table that has a parentheses around the atomic mass, it's because it doesn't occur naturally. You have to, so there's those numbers up there assume that they occur naturally. We measure their natural amounts on Earth, and we can calculate an average atomic mass. If they have parentheses around them, it's completely artificial. And a lot of times we can't make a large enough amount to see what the bulk properties are. Like, we can make a tiny bit of polonium, but if you don't have a big chunk of it, you can't see that it's shiny and metallic if it's metallic, you know? So sometimes it's hard to measure these properties, and so they go unknown for a while. Anyway, since we can't see these, I'm going to skip these. And I think we've done this, but just to remind you, when you're counting atoms inside a unit cell, simple cubic always has 1. There are 8 corners, each count as an 8, so 8 times an 8 is 1. Body-centered cubic has the corners plus the one in the middle, so 2. And face-centered cubic has 6 face atoms. And each counts as a half. They're half in that unit cell and half in a neighboring unit cell. So 6 times a half is 3 atoms, plus the corners, it's 1 more, has 4 total atoms. Why do we need to know that? Well, we can do things like calculate well, in this case, this one is calculating the volume of a unit cell based on the radius of the atoms. So any volume of a cube is the side cubed. Length times width times height. They're all the same for a cube, so it's just that side cubed. But if you translate that to based on the radius of the atoms inside the cube, for simple cubic, that's the volume formula, based on whatever radius of the atom is making that structure. That's for body-centered cubic, and that's for face-centered cubic. And again, you don't have to memorize this at all. Just be aware that they are different for the different unit cells. I don't have to look them up and use them. So we used them to do this, which was calculating the density of lead. So question 21 was not that, but question 21, we calculated the packing cell efficiency. So the packing efficiency of the unit cell. And again, the exact numbers don't matter. What you should know is the relative order. Simple cubic is going to have the most empty space. It's got a low packing efficiency. Then body-centered cubic, then face-centered cubic is going to have the highest packing efficiency. So those are the numbers we calculated. You don't have to memorize those. Just know the order. That's all. Here's the question when we calculated the density of lead. So we did this already, so I'm not going to do it again. But the idea is instead of doing a mass and a volume on a large scale, we're doing mass and the volume of a unit cell. It's a really tiny scale. And it works out, you get the same density as long as you have the right numbers. So, so we did mass of the unit cell, volume of the unit cell. The volume of the unit cell is going to depend on a couple things. Sometimes you have to know the radius of the atom, and then you take one of those previous equations, plug in the radius of the atom into that equation, get the volume of the unit cell. Sometimes you're given the side of the unit cell, S, that's literally the side of the unit cell. So you just cube that and you get the volume of the unit cell. So pay attention to what information you've been given. For the mass of the atoms, you just need to know how many total atoms are inside that unit cell. Figure out what is the mass of each atom. And you can get that from the molar mass. Turn the molar mass into an atomic mass. Not AMUs, you want the mass of an atom in grams. And so when you do it, you get a number that matches the actual density of lead. And this is just showing how we did it. These are the units. Sorry.
Okay, can I actually,
Yeah.
I need this.
Yep,
I
yep,
missed
yep.
that last week.
So this is the top part. This is calculating the mass of the atoms in the unit cell. So you've got your molar mass. You divide by Avogadro's number to get grams per atom. And then you multiply by the numbers of atoms in a unit cell, and you'll get mass per unit cell at the end.
Cool.
Okay, so why don't we try this? Let's see if you can do this yourself. As a group, you can work with other people, but let's try to calculate ultimately the density of molybdenum, which is MO on the periodic table, number 42. And I'm giving you that molybdenum has an atomic radius of 136 picometers. That's the radius of one atom. And it does body-centered cubic crystal structure, BCC. So using that information, plus the periodic table, first calculate what is the length of one side of the unit cell. And then using that information, what is the density of molybdenum? Our density has units grams per cubic centimeter. So take any length, convert it to centimeters so that they match. And I'm happy to help somebody start if they have no idea. So body-centered cubic. And it's molybdenum. And the radius is 136 picometers. So that's the main information. So we want the length of the unit cell, S, and we want the density. I'm going to give you a hint. I'm going to switch to workbook. Actually, no, let's not switch to workbook. Let's go back a few slides here. There, these equations will help. Well, no, I guess we don't need that. If we want the length of a side, those aren't going to help. We want this one. Where is it? Back to here. Here we go.
4/3 squared.
That is the side of a unit cell for body-centered cubic is that.
Am I going in the right direction?
Yeah. Well,
Well, that was what I actually.
so that is fine. Before you convert to volume for the next part, I would convert picometers to centimeters to make things
Centimeters,
easier.
okay.
Before you do any volume calculations. Yeah.
I gotta catch up on this.
So this radius is in picometers.
Try to catch up.
But like, I need to convert it to what
I don't know
equation
this
with the radius.
So in this equation, it doesn't matter what unit you plug in, you'll get the same
Oh,
unit for your side.
Yeah.
'Cause I'm gonna be.
I just didn't know if you want.
So I guess for the side, it doesn't matter. Maybe we can use the meters, but when you do density, you'll have to convert that length to the centimeters. I'd say this is the hardest calculation you'll do in this class. So if you can get through this, this is not too bad. You're not trying to be a math class. This is it. Okay, and if you use that equation for radical 3r to get the side.
Oh, the second one, or the first one?
Yes, the one at the top is simple cubic. This one in the middle is body center cubic, which is what our molybdenum is in. It's body center cubic structure.
Okay, but this was the length.
Yeah, so S is the length of one side of the unit.
Oh, okay.
Yes.
And then how do I get the density? So I adjusted it to
Okay.
centimeters, and then how do I get density?
So that's the side of a cube. If I have a cube, and I know this is S, and that's S, and that's S,
yeah.
the volume is going to be what?
Like times F of height.
S cubed.
Yeah.
So cube that to get the volume.
Okay. So then okay.
And then you're going to, density is mass over volume. So you'll have the volume of the unit cell.
And then I have to
You just need to find the mass of the atoms inside the unit cell. So body center cubic, how many atoms are there?
Oh, there's 3, no 2.
2, right. So can you figure out the mass of 2 lead atoms in grams?
Yeah.
That's that thing you took a picture of before.
Yeah.
That's
So
what
look
you
at the
use.
molar mass and then adjust it down to
Mhm.
Avogadro's number and then calculate it. Okay.
Exactly.
What's the element?
Molybdenum, MO, number 42. Oh, yeah. So that would be for, so that is taking this formula and cubing this whole thing so that you get the volume of the unit cell from the radius. So, let me see if this helps. So there are 2 ways to get the volume, okay? You can use the formula that we figured out on Monday. So if you cube this, it becomes 64 over 3 radical 3r cubed. You can use this, plug in the radius into here and get a volume. Or you can get the side that you calculate, the length of the side of the unit cell, and then just do the side cubed. They both do the same thing. So if you know the side length, you just cube it. If you know the radius only, well, you can plug that in here and then find the volume too. But convert to centimeters before you plug it in, because otherwise it's a little bit more hairy to convert centimeter cubes. Yep.
Is part B the question? What is the part?
Oh, part B was there it is. Density.
Oh, okay.
All right, should I start to do it, or do you guys need more time? Okay. Yeah. What are you trying to do? Do this radius. That seems
This is a
incorrect.
picometers.
It's what?
This is a
Oh,
I can make that centimeters.
seems big still. But maybe. That seems really big, but it could be.
I have a question. So you're getting the density,
Uh-huh.
you sort of have this in, does that look like?
Yeah, I think so, yeah.
Okay, how do I go about,
So now density is the mass over volume. So you need the mass part
so I
now.
got the mass of one, I guess, mole.
That's the mass of mole, which is Avogadro's number of atoms.
So I need,
So how do you convert, so it's grams over moles. We need to convert the mole denominator into per atom.
okay.
Does that make sense?
Yeah, I'm
That's Avogadro's number, 6.022 times 10 to the 23rd. It's the definition of 1 mole. Anything you want to count is that many things for every mole.
I can't remember, picometer, was it 12?
10 to the minus 12, yeah.
Okay.
Okay.
I don't have to do that.
You getting anything reasonable?
I don't know.
That exponent is not quite right.
That was not right?
Yeah,
Okay.
so the volume, go back.
Right there, just
Cube
this.
the whole thing. 10
Yeah.
times 10 to the minus 8. When you cube it, it's going to be 10 to the minus 20 or something like that. It's going to be a really tiny number.
Wait, did I do it right on my calculator?
Oh, for volume? Or
How about
like,
I'll just
for
redo
density?
it. I'll just redo it.
Yeah, that,
That-
up here. Yeah, that looks.
So that looks right? That's the volume, that's the,
One of them is wrong. Hold on.
that was the one that you said that was the volume of an accident.
Think here. Let me do the volume and I'll tell you because I don't know what the actual number is at this point.
See so many numbers all there.
So side is 314. The volume is cube. Actually, I'm going to convert this first. Okay, that's my volume.
I probably did it wrong, but I got 1.23 times 10 to the negative 29. Maybe it's because I made it into centimeters before I made it into a volume.
That shouldn't make a big difference. Does anybody else get that volume, or did I make a mistake?
I thought it.
No, hold on. It is 4 over radical 3, right? I didn't write that wrong. Yeah, I think it is. 4 divided by radical 3 times 136 picometers is 314. If you convert 314 picometers, well, let's go all the way. Here, I'll use the other equation. I'll use that one now and see if I get the same answer. So the radius in centimeters would be 1.36 times 10 to the minus 8 centimeters. And if I plug that in here, I get 64 over 3 times radical 3 times this number, 1.36 e to the negative 8 cubed. And I get the same number, 3.09. Okay, I get 3.098 using this equation, but it's pretty close to that. So that should be your volume, and if you're not getting that,
Just put in, like, there's something wrong with
well, it might be order of operations, like you have to put parentheses around the denominator or something, or you know, maybe you need to calculate each piece and write it down and then put it all together. Something with how you're putting it in a calculator is getting messed up. So I think we could work on that after, or when there's a little bit more extra time, but make sure you know how to use whatever calculator you're going to be using on exams and quizzes, okay? So there's the volume. Now let's do the mass of the atoms. And we'll use the molar mass right on the board over there, 95.94 grams per mole. And we're going to convert this to grams per atom using Avogadro's number. And then I'm going to multiply by the number of atoms inside a BCC unit cell. So body center cubic has 2 atoms inside. The central one and the 8 corner pieces, which add up to 1 also. So 2 atoms per unit cell. So 95.94 divided by 6.022 e to the 23 times 2 gives me 3.186 times 10 to the minus 22 grams per unit cell. So that's the volume per unit cell, that's the mass per unit cell. So now we put them together. Density is 3.186 times 10 to the minus 22. And the volume was 3.0, read that right, 96 times 10 to the minus 23 centimeters cubed. Divided by 3.096 e to the minus 23. And I get 10.29. If you're familiar with densities, that's reasonable for a metallic density. It's pretty dense. So if we look it up online just to make sure, or actually we don't have to look it up. Here's the math. So that's a picture of molybdenum. Body center cubic. The colors don't matter. They're just showing the differences. That's it. They're all molybdenum atoms. So 314. There should be an equal sign there. Yeah, I don't know why there's not. That equals 314 picometers. Then you convert for picometers to centimeters. So they did it in one step instead of 2, but there it is. Then we get the mass of all the atoms. There it is. Then we divide, and you get 10.3 approximately. And if we look it up online, we might as well do that. Molybdenum. Can't spell it right. Molybdenum density is in here. Let's see. See what Wikipedia says.
Does it say 3? Does it say 3.186?
There it is. Which one?
Oh, that
3.096 in the denominator, yeah. So yeah, 10.28. Pretty close. So I don't know where that comes from. It's not cited, but I'm sure it's pretty good. All right. So we did it once. You can see it's tough. You got to practice it. Make sure you understand how to use your calculator. You'll get it in homework, I promise. Any questions about this? Not sure why I did something. All right. Okay. So we talked about this already, so I'm going to skip this. But this is, you don't need to know the specific numbers, you don't need to know the specific equations, you just need to know how to use them. I'll give them to you if you need them. All right, so we've kind of looked at some of this already, but let's review it again. Metals tend to form crystal structures with high packing efficiencies. So these are all metallic. The gray ones here are body-centered. The black ones are face-centered, and we didn't really cover these. The vertical lines are hexagonal, which are also high packing efficiencies, similar to SEC. Very few of them have the simple cubic. So polonium is one, but that's it. And we know that it's because metals like to be around a lot of, don't mind having high coordination numbers. So let's look at Chem Activity 24B. And I think these are good to do by yourselves, or at least in small groups. We're just going to do questions 1 and 2. And I think it's probably around page 36, but I don't know exactly what page it is. So, 24B, 1 and 2. You like a binder?
Yeah, thank you.
And we also need a binder.
I'd like a binder.
Let's see if we have any.
Wait, there you go. That's what you say. Yeah.
These have been here for like years, so.
Honestly, I just keep using the same binders from term to term. Yeah. I don't know what to do. I try to collect everything every term.
I guess I usually get a binder here, with a folder because then I have room. What? Is this your Friday? That's like, it's not bad. I don't really do stuff Fridays anymore. I'm doing work most. No, I just
I'm playing cat noises through my entire home speaker system right now to mess with my animals. I don't like it when they're home alone all day. So I like to play angry cat noises and angry dog noises to try to scare them. They bark at everyone that comes to the door dropping off packages.
It's good for burglars too, yeah.
Yo, because she's one of those dogs that like will bark, and then the moment someone like steps foot into the door, it turns into a wagner.
Cower. Oh, yeah. Pavlov's bell. I'm trying to do that when I hear people.
It's really horrible, that's a real thing.
It's actually what music do.
There's literally a...
It's not even a horrible thing. It's like kids they can control it. They just don't know the access to it.
That's why like when I like my research, I openly state in my Jinso because I personally feel that because...
I'm not saying actual dogs. That was horrible. I'm not just doing it. No more.
Oh yeah, people.
Yeah, sit down there. If you want to get to me, they're randomly mixing that much.
The coordination number is the number of atoms that any atom.
You might like psychology.
So,
That is messing with people.
well, so for body center cubic, that center one is nearest to the 4 on top and the 4 on the bottom. So, yeah. And even though it's harder to see, you even look at the corner atoms also touch the other atoms too. any atom touches that many atoms.
Since
Yeah.
the body center cubic is only the one in the middle and the corners, so there'll be 4 atoms and it's touching the entire thing. What it says is the body center.
All right, let's talk about the answer. I think people have looked at it. Some of these are easy. I think some of them are maybe a little challenging, but coordination number for tungsten, if it's BCC, there's 8 atoms touching every other atom inside tungsten.
Body center?
So the center one is very easy to see that the center one's touching the 4 corner, or 8 corners, excuse me. But even the corner atoms, if you expand the crystal and see what the neighboring unit cells look like, the corner atoms also touch 8 other atoms. So everything touches 8. For FCC, how many? 12, yeah, 12. FCC is always 12. Every atom touches 12, whether it's a face or a corner. They all touch 12. That's a little harder to see. You need to play with the model to see that. But so layer diagrams. You know, I'm sure you just looked at the one that was in the previous page and copied it, but you know, you should be able to write these yourself. So layer diagram for BCC, you have atoms in the corners, and that's it, the bottom layer. And then there is an atom at the center. So the center is the halfway layer, 0.4, 0.5, and there is an atom right in the middle. That's the layer diagram. So remember, the bottom layer is always the exact same as the top layer, so you don't have to draw it twice. So how many atoms per unit cell of potassium, BCC? There's 2. Pretty standard. Doesn't matter what atom it is, as long as it's BCC. FCC, unit cell diagram. All right, this one's a little harder, but FCC, there's always the corner atoms. So that's the bottom. But there's also the face in the very bottom layer. There's a face atom right here. This is actually hard for people to distinguish. That's a face atom, that's a central atom. They're different because of the layer they're on, okay? And so what else do we have? Well, halfway up, there's a bunch of face atoms. And they are here, 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 and here. And then the top layer is exactly the same as the bottom layer. There's a face in the middle, and there's 4 corners at the top layer. So that's BCC, that's FCC. So we're going to add to this in a little bit. Okay, I already showed you diamond. You can see we're going to modify these. Oh, how many atoms per unit cell of silver? 4. Just because it's FCC, 4. Okay, so hopefully number 2, if you got this far, lit up a light bulb. The packing efficiency versus coordination numbers, okay? You can see that as we go to higher coordination numbers, we go to higher packing efficiencies. That should make sense to you. If we have one atom that's able to touch 12 other atoms, we're packing those atoms really close together that it can touch that many other atoms. Whereas simple cubic, one atom only touches 6 other atoms. And so the atoms are not packed super tightly together. It's only touching 6. So it's got a lower packing efficiency. Okay. So we saw this already. We saw this. This is a nice FCC structure with methane. And again, I want to point out that we call the positions in a unit cell in a crystal structure lattice positions. We don't call them atom positions because they don't have to be populated by atoms. You can put a whole molecule in that position. So that's why they're called lattice positions, not something more specific, okay? All right, so we looked at this already, but you know the key point here is that semimetals, and that does include carbon, even though carbon's a nonmetal, but because the electronegativity is not super high, it's it's high, but it's not very, very, very high. You get these states where they still want to do kind of localized bonding. They have a high enough electronegativity that they really do like electrons. But they don't have many electrons. And so we know carbon from 221, carbon likes to make 4 bonds in a little structure. And because it can do that, it can go in all different directions when it bonds. you can start to create these really large structures, and that's where these covalent networks come from. They are covalently bonded, but you can have a whole bunch of bonds going in all these different directions. So yeah, that's when you get to these intermediate electronegativities, they start to do these covalent network type bonds. So silicon does that, even though it's a semimetal. Arsenic and tellurium and germanium and boron all do that. So we did look at the diamond structure very briefly. Diamond is a network of single bonds, 4 single bonds per carbon, and they're all tetrahedral arrangement.
Sorry.
Yeah.
I don't want to jump ahead or anything like that, but is there a reason? You know how like diamonds have different things, like different types of diamonds, I guess, like grades, or like there's like a
Well, the
purity-
colors and purities, yeah.
Purities.
Uh-huh.
Is any of the structure have to do with that?
It has to do with flaws in the structure.
Okay.
So any colors come from random metals being inserted somewhere in the crystal structure, and it's imperfect when it's that. You know, like you're breaking this perfect structure here. So yeah, it's just impurities. If it was a pure diamond, it's just this, and it's just clear,
Yeah.
colorless.
And that's why man-made diamonds, which are technically perfect in structure, but are still not the same chemical component.
I mean, I think they can figure it out. Like, if they're too perfect, they probably could, or probably are synthetic. But synthetic diamonds are chemically the same.
Yeah.
They are exactly the same as regular natural diamonds. I think when all the people that make synthetic diamonds have made multi-billion-dollar deals with the diamond mine people to limit their supply and to do things like put fluorescent tags inside their synthetic diamonds, or engrave little serial numbers on their synthetic diamonds so that they're easily recognizable. So I don't know, there's like, I've seen videos where this guy punch up people, like they check to see if the diamond's synthetic or if it's real, you know, they're the same. And they put them in a machine, and I think what it does is it just bathes it in UV light, and you see the fluorescence. So the synthetic diamonds usually have something inserted on them that causes them to fluoresce, and that they can pick that up and tell that they're synthetic because of that. But synthetic diamonds are chemically the same. They just they on purpose add stuff to them so that they don't get assassinated by the De Beers company. So yeah, I mean, De Beers.
I am taking you serious on that one, because that actually seems kind of legitimate.
This is conspiracy theory crap, but I mean, De Beers limits the supply. If they flooded the market with diamonds, their value would go down.
Well, it's just like you know, I'm not trying to say anything particular to go into it, but it makes sense because
Well,
because we are moving
he
towards
assassinates
the day and age where we are easily going to start replicating
Yeah.
or reproducing new things, and that could also include fossil fuels, and that's dangerous in our economy. But
well, they
is
do
what
that
it
with
is.
biodiesel,
Yeah, no.
right? So yeah, no, we can make synthetic diamonds, and there's plenty of companies that figured out how to do it.
Oh, easily. Diamond's the most common thing there is.
Yeah, I mean, we use it for tools. Yeah.
They're just wildly overinflated.
Yes, they are ridiculously dumb in terms of how we value them. I mean, yeah, they're pretty, and they're strong, they're useful.
Oh, very useful.
Yeah, they used to be rare, not anymore. So, to make the diamond, I'm going to reiterate, it's a FCC structure that has been expanded slightly, and there are pockets inside we call tetrahedral holes. So these pink atoms, which are not atoms, these are the positions where you would put an atom. We call them tetrahedral holes. They're called tetrahedral holes because if you isolate one of them, so look, we're isolating this front one here, there you go. This position is nearest neighbors to only 4 other lattice positions in a tetrahedral arrangement, and that's why it's called a tetrahedral hole. So, how many tetrahedral holes are present in an FCC lattice? And if you need a clue, there we go. I'm training you guys to get your clickers recorded for the fix.
And then they shut off sometimes too, so you're like,
Um,
oh my God.
the batteries. I know that when they get semi-low, they'll flash red, but when they get super low, they'll just die instantly. But we could try them. All right, so we got a few answers here. The true answer is 8. Okay, so I know that maybe some of us are jumping the gun. In an FCC lattice, there's 8 holes. 1, 2, 3, 4, 5, 6, 7, 8. Not all of them are used sometimes. All right, so when we look at the diamond structure, let's do the Z-layer diagram for this cell, just to have it clear. Well, we're going to start with FCC. So your Z is equal to 0 layer. You have your corner atoms, and you have your face atom. But the next layer that we're going to draw, we are all drawing any layer where we can cut through atoms. So this is the next layer. And so that would be approximately 0.25. There's an atom here, an atom here, an atom here, or a position here, I should say, an atom, a position, a hole here. The midway layer, that's standard FCC. We've got our face, 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 around the middle. And then we've got our second set of holes. 3/4 of the way up. And same places, here, here, and here. And then our last top layer is exactly the same as the bottom layer. So this is the layer diagram for FCC with the tetrahedral holes present. So here's where diamond comes in. We have to consider this structure and use that to generate diamond. The diamond structure is only half of those tetrahedral holes are occupied by atoms. So here we're showing all of them. There's 4 down here, 4 up here. But here we've only got 2 up here and 2 down here. Only half of those holes are filled up. And so there's the layer diagram for diamond. You can see the difference. We've only got 2 atoms in this layer and then the opposite 2 on this layer. And so if you consider, for instance, this particular whole atom, it is nearest neighbor to the corner atom, the face atom in the bottom layer, and the face and face in the middle layer here. That's very difficult to see, I think. So that's where we have our Lego models. So let's look at 3A to 3G. Hopefully the Lego models will help you see them. Everybody has one. So go to the same connectivity, 3A to 3G. Let's do that for 5 minutes. It looks like this. Make sure this is clear. So yeah, these Lego models, these are of the diamond structure. It is every FCC position plus half the holes filled up. And you might have to share, sorry. Lego is a cheap way to have a lot of them. They're not that cheap, but.
And they hold their value. They're
Yeah.
they're amazing.
Still cheaper than a real model.
Yeah.
Scientific stuff is at a premium because it's low supply, low demand, I should say.
That's sad.
Yeah, equipment is like so expensive. It's all specialty. You don't build lots of it, so you have to charge a lot. Yeah.
It works really well at that, like, the bounce off of it is actually absorbed.
Okay. Some of these are, I think, pretty easy. Some of them are not as easy. So A, I think, is not the easiest, but how many atoms are there inside the diamond unit cell? Do they have a number?
There are 5. 4.
A little bit more than 5, more than 4. So this is based on FCC. How many do FCC have? 4. But in addition to FCC, what are we adding? We're adding the whole atoms here and the whole atoms here. Are they inside completely, or are they partly shared? I mean, look at your Legos. Are they shared outside, or are they all the way inside? They're all the way inside. So I've got the 4 from the FCC part, the corners and the faces, plus I've got 4 more from the inside holes. So 1, 2, 3, 4, all the way inside. So I've got 8 atoms inside this unit cell. So when you do density calculations for diamond now, 8 atoms. You don't have to do that one, but you could do it. So how many bonds does each carbon make? 4. That's pretty natural. Carbon can't really do more than 4 because it only has s and p orbitals. That's the max number of bonds it can do. It can only have an octet. It can, it just needs 4 extra electrons. That's it. So the coordination number is 4 as well. It's got 4 bonds. The max coordination number is 4. You could have a smaller coordination number if you did like double bonds and stuff, but that's not in this case. Okay? Yeah.
I was thrown off because it says look back at the SEC structure, and so I thought it was only supposed to count the 0, half, and 1. I guess it, and so I was only counting, and
I think what they're trying to make sure you do is not count the FCC atoms as whole atoms. That's all. So just to remember that the corners count as an 8 still, and the faces count as a half.
Okay.
Maybe that's, yeah, I understand how to throw you off though. Yeah.
Okay.
But yeah, the ones in the center, the new ones, they're completely inside, so we count them as whole atoms. All right. D, what's the coordination geometry? Tetrahedral, perfect. I mean, you can see it on your Legos. The holes are tetrahedral with the corners and the faces. How many valence electrons does carbon have? 4. So stands to reason that things that are similar might have a similar structure. They would bond the same way. So what other elements have 4 valence electrons? Yeah, group 14, everything underneath carbon. Silicon, germanium, to some extent tin. But let's ignore tin for a second because tin's a metal, so that's a little bit more complicated. But silicon and germanium actually have this structure too. silicon. And so if you were to rank them in terms of their unit cell size, what's the smallest, what's the biggest? Yeah. You guys know trends from the periodic table. As we go down the group, they have bigger shells, they're bigger atoms because they have more electrons. And so that's going to get reflected in their unit cell size too. If you have big atoms, they're going to make bigger unit cells. They have to fit, they have to butt up against each other, so they're just going to make a bigger cell. All right.
I just have a question.
Yeah.
Why did you draw 4, like in the 0.25 and 0.75, but the picture on the sheet has 2? Like in
Oh, in your sheet.
Yeah.
So this is the idea that an FCC structure has the potential. It has space for 8 total holes. So every one of these positions is an actual tetrahedral hole. But for diamond, only half of them are used. Does that kind of make sense? So
that's not for diamond, and this is for diamond.
this is not for diamond. Yeah, this is just this is how we think of, well, how does diamond do this? Well, we pull everything apart. There's bigger spaces now, and those spaces are called tetrahedral holes. Sometimes they're all used. It depends on the structure, but not diamond. Diamond only uses half of them. Okay. So I guess that Tim does do this. Wasn't quite sure about that one. I forgot that one. But yeah, anything in that group, because of 4 valence electrons, will tend to make this structure. It's ideal for it. So silicon. Here's silicon. This is the same as diamond. We're only showing you, not even the unit cell, we're just showing you a piece of silicon. And silicon has 4 nearest neighbors. 1, 2, 3, 4 in a tetrahedral shape, just like diamond does with carbon. So these network covalent solids have a much smaller coordination number. And they have to have this smaller coordination number because they only want 4 extra electrons. They don't want too many more. And that would, having too many nearest neighbors would give them too many electrons. Okay, so let's talk about some more complicated crystal structures. We're going to talk about isoelectronic solids now. And to understand isoelectronic solids, let's remember what isoelectronic means in general. Isoelectronic means same number of electrons. Iso is the same. So an isoelectronic ion means you have the same number of valence electrons. So fluoride and oxide are 2 ions that are isoelectronic. F minus, O2 minus. They both have 10 total electrons, 8 valence electrons. Okay, that's an isoelectronic ion. Isoelectronic molecules. What does that mean? Well, you've got molecules with the same number of valence electrons. So what does that mean? Well, N2 and CO. If you count the total number of valence electrons in nitrogen, each nitrogen has 5 valence electrons. So 2 nitrogens has 10 valence electrons. Well, CO, carbon monoxide, carbon has 4 valence electrons. Oxygen has 6. 4 and 6 is 10. So they both have a total number, total number of valence electrons, 10. These are isoelectronic molecules, an example of isoelectronic molecules. All right, so we know what these are. Now let's go to isoelectronic solids. What does it mean to be isoelectronic as a solid? So solids with the same number of valence electrons, on average. We can't count billions of electrons because we're going to have a big bulk of a whole bunch of atoms. So we're gonna focus on an average number of electrons instead of the total. So if I were to quickly ask you what species down on the list below would be isoelectronic with nitrogen, N2. number of valence electrons, basically. All right, I'm gonna stop it at 60. Okay, so stop it there. The votes go all over the place. That's fine. It was a little fast, maybe. So the answer is all of them are isoelectronic. Nitrogen has 10 total valence electrons. Nitrogen has 5. It's 5 over from the left side of the periodic table. 2 times 5 is 10. Cyanide. Carbon has 4, nitrogen has 5, that's 9, plus an extra electron from the minus charge, 10. Boron has 3. Fluorine has 7. 3 and 7 is 10. Each oxygen has 6 valence electrons. 6 and 6 is 12. But the plus 2 means we've lost 2 electrons. So 12 minus 2 is 10. 10 valence electrons. They all are the same. Isoelectronic. Okay. So that's just an exercise to make sure we understand isoelectronic, the term in general. Well, there's another one. If I were to replace the O in H2O with a carbon, how many total hydrogens would I have to go with that carbon? This is another exercise in isoelectronic, but now isoelectronic molecules. We're trying to make isoelectronic species here. Somehow, having the same number of electrons makes it a stable molecule. You can come to this conclusion from a different angle as well, but so if that doesn't make sense to you, how many hydrogens should carbon have? That's a valid answer too. All right. So most people said D. Yes. Carbon should have 4 bonds, so 4 hydrogens. But let's look at it from the isoelectronic molecules perspective. If I count total valence electrons, 6 plus 1 and 1 is 8 total electrons. So somehow 8 electrons in a very simple compound like this is stable. Well, you could do the same with carbon. Carbon has 4 valence electrons. Well, we need 8 total. So each hydrogen contributes 1. You would have to have 4 hydrogens to get 8 electrons. This is just another way to think about how to make something stable. So instead of thinking purely, octet on the central atom, or, that's the way we've thought in 221. This is another way to think about it. Isoelectronic total electrons, somehow 8 is stable. And that's what we're going to do for the next step. We're going to think in terms of isoelectronic. That's how we're going to determine what species are possible in reality. And so here are some great examples. This is benzene, C6H6. You guys have seen this before. It's a very stable structure. It's everywhere in organic chemistry. That particular thing is toxic, but it's in steroid, it's in estrogen, it's in lots and lots of things. It's in amino acids, and it's fine. So if I replace, so remember, carbon has 4 valence electrons, and I've got 6 of them here. So that's, if I ignore the hydrogens, that's, well, I can't really ignore the hydrogens, but if I ignore the hydrogens, 6 times 4 is 24 electrons in that ring. Well, what if I replace half of the carbons with nitrogen and the other half with boron? So 3 borons, 3 times 3 is 9, and 3 nitrogens, 3 times 5 is 15. 9 and 15 is 24. Same number of electrons as the carbon ring. That is actually a real thing, borazine. And the way we thought about how this could exist is the concept of isoelectronic. 2 things being isoelectronic. So let's expand that. So we'll go from simple molecules to more extended structures. This is graphite, which is basically carbon rings in this hexagonal format. Well, I could do the same thing with boron and nitrogen and make these hexagonal rings out of boron and nitrogen. And this stuff exists too. Let's make it even, let's take it a step further. Instead of 2D, let's go 3D. So diamond is, you've seen diamond, it's all carbon. Well, let's take half of those carbons and replace them with boron, and the other half we'll replace with nitrogen. And you get this thing called borazon, which exists as well. So notice how the average number of valence electrons in this structure is 4. Everything has about 4. The average number of valence electrons here, half of them are 3, the other half are 5. On average, it's right in the middle, 4. So this average number of valence electrons is how we're going to start thinking about structures, okay? So let's say I took we know already that carbon and silicon and germanium and tin, everything in group 4 or 14A has the diamond-like structure. And they all have 4 valence electrons. So if I took germanium, and instead of using germanium, half of those germanium atoms are replaced with gallium, what other element would I have to replace the other half with to make an isoelectronic structure? So I start with germanium, and I take half of the germanium atoms, replace them with gallium. The other half of the germanium atoms, what other element should I use to make a similar stable structure? So germanium is Ge, gallium is Ga. This is where it gets a little tricky. Let's see what people are thinking so far. So, we got a little bit difference of an opinion. There's only 3 votes, so it's okay. Alright, somebody's going with majority rule. That's okay. So the answer is B, arsenic. And the idea is germanium on the periodic table has 4 valence electrons. So originally every atom in this crystal was 4 valence electrons. So on average, 4 valence electrons. If I take half of those atoms, replace them with gallium. Notice gallium is 1 step to the left, 1 fewer valence electron, 3 valence electrons. And the other half would have to average out to 4 still, would have to be arsenic. So, which has 1 extra valence electron versus germanium. So again, the key is these diamond structures are happening because everything has 4 valence electrons. 4 valence electrons, everything makes tetrahedral arrangements, 4 bonds. So to continue with that, everything still has to have, on average, 4 valence electrons. Yeah?
I'm just still kind of confused. So, germanium has 4 valence electrons, and it's replaced half with gallium, and so gallium has 3. So we're trying to make it an average of 4?
Yes, yes. So if this is your structure, and it just keeps going, the diamond structure, this has on average, everything is 4 valence electrons. I'm going to take half of these, and I can't really do half because I did 5, but I'm going to take half of these and replace them with something that has 1 fewer valence electron. Gallium has only 3 valence electrons. So to keep an average of 4 valence electrons throughout the whole crystal, the other half of my atoms have to be something with 5 valence electrons. So if half of them are 3 and half of them are 5, on average you'll have 4 valence electrons still. So I could make a structure with gallium and arsenic. It's called gallium arsenide, GaAs. And that theoretically should have the same crystal structure as diamond, because on average, this has 4 valence electrons still. And this is actually what's in red LEDs. This is the compound we make our all the LEDs out of. This is a perfect semiconductor for that. Now, why do we pick arsenic? Because it's group 5. Could we have picked phosphorus?
probably.
Yeah, you could use anything in group 5 as long as it has the 5 valence electrons, and then anything from group 3 as long as it has the 3 valence electrons, and pair them together to have, on average, 4 valence electrons. So again, there's something special about 4 valence electrons. We're going to study that exclusively. That makes these structures. Yeah.
Does it matter? I know you just said any, so obviously it doesn't matter, but why doesn't it matter that it's like a semi-metal or if it's a non-metal or a metal?
So, in this case, the elements we pick will definitely change the properties of the material that we're going to create. It'll make different colored LEDs. It'll have slightly different bonding. It'll be a different size of crystal. But because they will average out to having 4 valence electrons overall, they're going to keep that diamond-like structure. That diamond-like structure is, the requirement to have that diamond-like structure is an average of 4 valence electrons everywhere. So that's the key here. So what about if we extend that idea? So now I'm going to take my germanium material that looks like diamond. It has the diamond structure, germanium. And I'm going to replace half the germaniums with zinc. What do the other half have to be replaced with to keep that diamond structure? Okay. Let's see what people are thinking. All right. We have at least some good news here. The answer is D. So the idea here is I'm doing the same thing. Germanium has 4 valence electrons. If I take half my germanium atoms in my crystal and replace them with zinc, which has 2 fewer valence electrons, then the other half, to maintain the average of 4, should be replaced with something like selenium, which has 2 extra valence electrons. And then you will still have an average of 4 valence electrons. So if I combine zinc and selenium, I should still have a diamond-like crystal structure because on average I'll have 4 valence electrons still. And this is really, really weird because you're starting to go from semi-metal, that looks like ionic, metal, non-metal, but it still does that diamond-like structure. And you can still get kind of semiconductor-like properties out of it. It's weird. This is why we're doing shades of gray now. Nothing is purely ionic, nothing is purely covalent or anything. We have to think in terms of percentages almost, you know? Okay. So let's go to the extremes here. What if I take my germanium and replace half the atoms with copper now? What should the other half be replaced with to maintain that diamond-like structure? Yeah, look at the periodic table, stare at it. Count the number of spots you're moving. All right, we're more confident now. So, most people vote A. And yes, in this case, it would be A. Copper from germanium. Copper is 3 spots to the left. So, 1, 2, 3. So I'm going 3 fewer valence electrons than normal. Well, my other element should have 3 more electrons than normal, so I should go 1, 2, 3, all the way to bromine. Copper bromide. And I'm not balancing it properly, like with the charges and stuff. But if I somehow were to make a material that is made up of copper and bromine, that should also be diamond-like structure. If it follows the rules, it has 4 valence electrons on average. It should be diamond-like still. This one's going to be weird, but that's the idea. Those are the rules we're going to follow. We're going to aim for making these structures, these compounds, or materials. We're getting to material science now, that have 4 average valence electrons, because we are specifically focusing on this diamond structure. There's something special about the diamond structure that we're going to study in this class. And we're not going to do anything else because it's too much. That's a whole class by itself, but we'll focus on this as an introduction. So yeah, complementary pairs. These are any of these groups can pair with each other to create these isoelectronic structures. And you know, I said, well, why not phosphorus instead of arsenic? Yeah, you could do gallium and phosphorus, and it will still be 4 average electron, or 4 valence electrons on average. You could do zinc with sulfur, and it would have 4 valence electrons on average. Doesn't matter. So, we're going to start looking at something called zinc blend. This is the name of a structure, and I don't know where the zinc blend name comes from. It's pretty old. But it turns out that this is a very similar to diamond-like structure. But instead of being purely one element, it is a combination. It is 2 elements, right? Zinc, and it's going to turn out to be sulfur. Zinc blend is actually zinc sulfide. And this is the basis for LEDs. That's why we're kind of looking at this, because LEDs are cool and it's the current thing. Solar cells, same idea. So if you like solar energy, this is all involved. So we're going to kind of look at here this structure. We're going to answer these questions. I think it's actually in the exercise. Oh, no, it's not. Well, let's answer these questions first. So if this is silicon carbide, which is got the zinc blend structure as well, which atoms are sitting in the tetrahedral holes? I mean, I already gave it away. They're the carbon atoms. Why? So that's the tetrahedral holes, and this is the FCC positions, FCC lattice positions. I think you can see that the holes are a little bit smaller in this model. So the smaller atom has got to be the carbon between silicon and carbon. Silicon carbide is silicon and carbon. It's got to be the carbon ones. How many silicon atoms are there in this structure, in this unit cell?
4.
Yes. So the silicons are the FCC positions, and FCC, there's 4, right? It's 3 from the faces and 1 from the corners. Yeah?
So, why, I thought all the SI atoms are the big ones. It looks like there's more than 4, so.
So remember, even though we're showing the whole atom, the unit cell part, we only count what's in the unit cell. So this corner, this atom is shared with 8 other unit cells. So this corner, only 1/8 of it is inside the unit cell. So let me give you a picture. Here. This is FCC. So if I actually were to cut away the unit cell part, that's what you'd see. And so this corner atom, only 1/8 of it is inside the unit cell. So when you count,
Each of those holes is 1/8.
yeah. So you shouldn't think of it as the whole atom is inside the unit cell. It's only 1/8 of it. This little piece is inside the unit cell. So a corner counts as 1/8. A face counts as 1/2. It's half inside this unit cell, half. So this one is half inside this, and half in the next unit cell above it. So yeah, the FCC positions is always 4 total atoms if you add up all the pieces. So 4 silicons. How many carbons? 4, yeah, 4 holes. So the formula, Si4C4, simplifies to SiC. That's the formula for silicon carbide. 1 silicon, 1 carbon. And so the coordination number for carbon or silicon, doesn't matter, is always going to be 4. Every atom in the diamond-like structure, or in this case, we're going to call it the zinc blend structure because it's 2 different elements. Every atom has a coordination number of 4. So notice the difference. This is diamond on top, zinc blend on the bottom. They are essentially the same. It's just the difference is one has two different kinds of elements in it. And so one of the elements will be in the FCC positions. The other element will be in the tetrahedral hole positions. But otherwise, they're exactly the same structure. And that's what these are going to look like. So these, where we use two different elements, these are going to have that zinc blend structure, which is similar to the diamond structure. Yeah, so there you go. Same, this is the layer diagram. We have time for this? Yeah, we have time for this. Let's finish this and then I think we'll be done. So 9 through 15 on, I think it's page 40 for you guys. And there's plenty of reading to do if you want to go back over this. So empirical formula, don't forget what empirical formula means. Empirical formula is taking whatever number of atoms you have and simplifying it down to the most simple ratio. That's the empirical formula, which is what we just did with silicon carbide. Okay, so this is the structure for zinc blend, and just like we did for silicon carbide, you could do this for this. You could say, right, so the white atoms, there's 4 total, these are corners, and there's 2 layers, right, the top and the bottom. So 8 total corners, times an 8 is 1. That's a face, bottom and top, so 2 faces there. These are faces, so 6 total faces. This half, they count as half, so 6 times a half is 3. So yeah, there's 4 total white atoms, and then these are inside, so 4 total black atoms.
So it would just be like, I don't know what like it stands for.
So,
It would just be Z and, I don't know.
well, you could just use generic names like this. So, A is going to be, well,
So it's AZ.
Yeah, AZ, because it's 4 to 4, or is it 1 to 1? Same thing. Yep.
And
Mhm.
the coordinate number?
Mm-hmm.
There's no inflection in the
Well, so, while this is diamond, it's almost exactly the same as this, except the hole positions, right here and here, are just different atoms. So, it's the same. The holes are touching 4 things, these 2 and these 2, and kind of need another unit cell to see everything else, but like this space is touching this hole, it's touching the hole down, let's see, well it's touching this hole, yeah, and it would be touching the hole on, oh, it would be touching the hole down here in this unit cell, and I think the one up here, the neighboring unit cell. So it'd be one down here and here. So yeah, everything's touching 4. So whether it's a FCC position or a hole position, everything touches 4. So 4.
Always, or?
Yeah, for this structure, it's always going to be 4. Yep. We will look at different structures next week in lab. But for lecture, we're going to focus on diamond and zinc blend, which are almost the same. We're going all the way to 15, but you know, if you don't get that far, that's fine. Let's actually talk about the answer so that we can leave on time. So 9A, the empirical formula is if you use just generic letters, A1Z1. It's just one of each atom. So in a 1-to-1 ratio. If you count the atoms, there's 4 of the FCC position atoms, and there's 4 of the hole position atoms. So 1-to-1. Whether you're a hole or you're in the FCC positions, every atom will touch only 4 other atoms. Doesn't matter which position you're in, you always touch 4. So the coordination number is 4. The geometry is tetrahedral. Same as for diamond, okay? They're showing in this diagram that the hole positions are generally a little bit smaller. So if I think about, well, what would be there between gallium and arsenic? So if you made a structure with gallium and arsenic, what would the holes be? Would they be the gallium or the arsenic? The arsenic. Because as you go to the right of the periodic table, things get smaller, right? You're adding more electrons to the same shell. Oh wait, I think I did that the wrong way. Yeah, you're adding more electrons to the same shell, but you're adding more protons. So the more protons make it smaller. For some reason I was thinking something else. So as you go left to right on the periodic table, things get slightly smaller. So this, the arsenic would be in the hole position. 11. Which solid from the following isoelectronic set of solids has the longest bond length? Bn, AlP, gallium arsenide, indium antimony. Antimonide, I think it would be called. Indium antimonide.
Last one?
The last one. It uses the biggest atoms. So if you're using the biggest atoms, you're going to make the biggest crystal structure, biggest unit cell. So which solid from 11 has the strongest bonds?
The first one?
Yeah. So we're not talking about ionic bonds here, but the idea still remains the same. The closer they can get, the more overlap the orbitals will have. And that's really what matters here, is how these atoms interact with each other. And so the smaller they are, the stronger the bond's going to be. Bn should be the strongest. So number 13, gallium nitride, gallium phosphide, gallium arsenide. These are really important. They all have an average of 4 valence electrons. Which one is going to be the most ionic out of these?
Gallium nitride. One with nitrogen.
Why gallium nitride?
Because nitrogen is the most electronegative.
Yeah. So when you think of the bond type triangle, what makes it ionic is the difference in electronegativity. The bigger the difference, if you have a low electronegativity versus high electronegativity atom, the bigger that difference, the more ionic it's going to be. So we want to pair up our slightly low electronegativity gallium with the highest electronegativity element. In this case, nitrogen is the most electronegative out of those 3. Yes?
I thought the reasoning would be because it's the smallest. Oh wait, it's not the smallest.
Well, the nitrogen is the smallest out of phosphorus and arsenic, yes.
Yeah. So I thought that would be the reasoning.
Well, you would use the size to talk about the strength of the bond, maybe.
Okay.
But in terms of the quality, what kind of bond is it? Is it more covalent or is it more ionic? Well, if we're talking about ionic, the way you gauge that is difference in electronegativity, right? That's the top of the bond type triangle. That's ionic. So this would be closest to the top of that bond type triangle. So which of these has the shortest bonds? GAN, yeah, because you have small. Smallest ones will make the shortest bonds. And which has the strongest? GAN, yeah. So we'll eventually take this idea of which is the most ionic, which has the shortest bonds, which has the strongest bonds, and we'll use these concepts to understand what color the LEDs might be, what kind of wavelengths do they spit out. You know, what color light do they make? All of that's going to be related, and we'll have a lab that focuses on that too. It's pretty cool. But before we get to that, we'll have to study molecular orbital theory and some other hair-raising stuff. But let's stop for now with this intro to the diamond structure and the zinc blende structure, almost the same thing. We'll talk about this next week. So quiz next week, same day. Don't ask me yet what's on it. It's probably going to be up to this, but I'm not sure how much of this is put on it yet. So let's see what we have to review next week before we decide. So homework, don't forget Monday homework and written homework on Monday as well. So online and written. All right. You guys have a good day.